Welcome back, ladies and gentlemen. This video is titled Newton's Third Law of Motion, but it's really more about how forces are affecting things when objects interact with each other. And one of the best ways to think of this is that forces come about, forces exist when two objects interact in some way with each other. If the objects are not interacting, well, there will be no forces between them. So always be thinking about that. We don't necessarily have to have motion to look at Newton's third law, but we definitely have interacting objects and the forces that those interactions really lead to. So be thinking about that. For example, here I've got a flower vase sitting on a table, and the table's on the floor. The floor or the ground can represent the earth. Cool. Well, if we were to look at the forces between the vase and the table, then we have to look at both objects, really. And I want to show you something here. It's kind of cool. What we're going to do is a free body diagram of each of those two objects. Free body diagram, the best way to look at forces in most cases. So just setting up two coordinate systems here for each free body diagram. So this is going to be the vase. This is going to be the table. So I'm identifying the object in question. And so what this means is I'm more or less, the flower, consider the flower part of the vase, sure. I'm more or less identifying that as one system and the table as the other system separately, right? Well, what are the forces affecting the flower vase? It has mass, and so gravity's pulling it down. In fact, let's talk about its mass. Let's say the mass of the vase is just not very heavy, 1 kilogram. I shouldn't say heavy. That refers to weight, but it won't be very heavy. 1 kilogram. Let's say the mass of the table is, 5 kilograms. Okay. So let's look at some forces. This is for the vase. So we have gravity pulling it down. Force of gravity. We know that the force of gravity, the weight, is always going to be mg. So this m is mass of the vase times g. Okay, and since if we know that stuff, we can find that value if we needed to. But we also know the vase is in equilibrium, which means that's right, forces are balanced. So I have this upward force that balances that downward force. That upward force, it is a normal force, to be sure. Now, the thing about that is what is causing that force? There's another way to look at this. That the normal force, we could relabel it if you want to. And this is going to help you see these interactions. This normal force, I'll put also known as the force of the table on the vase. The force of T on V, for table on vase. Okay. And I'm doing that to illustrate how these objects are interacting with each other, right? Well, how about forces acting on the table? This is a little more interesting. So, we know the table has its own weight. It's going to be pulled down by that. But the vase is pushing down on the table. How big is that force of the vase pushing down on the table? Well, that's equal to the weight of the vase, isn't it? So that force is pushing down on the table. So I kind of have to duplicate that force here. Now this is not the weight of the table. This is, so I can't label it force of gravity. I have to label this force of vase on table, don't I? And this is interesting right away. Look, I've got force of vase on table, and I've got force of table on vase. Okay, but there's more coming on. The table has its own weight, so I'm gonna change colors here, just to let this stand out, because these are two downward arrows. The weight of the table, well, it's going to be 5 kilograms. It's going to be a longer arrow. Let's draw off the side real quick here. I should draw that 5 times longer than that one, but you know what? I'm going to fudge just a little bit. This is the force of gravity, which I will show is the mass of the table times g. This is the weight of the table then. Okay, but the table is in a state of equilibrium, and that means forces are balanced, of course. So, I'm going to go back. I'll just go back to red, just because. Keep my forces red except for that guy, so you can tell those apart. How long do I draw this upward arrow? Well, it's got to balance these two downward arrows. So I'm going to estimate roughly. So it's going to be balanced by going way up there. And I have to add that. Oh, I'm way at the top of the page here. Way at the top of the page. Okay. So a little bit of a lack of planning on my part. I didn't realize it was going to be so huge. And so this kind of, on a side note, if you end up doing something like this, as long as you're neat and you're clear and it's still accurate, it's actually okay. It would be nice if it was redrawn somewhere with enough space, but neat, clear, correct, you're good to go. Now, what is that force, though? Well, it is a normal force, right? It is a normal force because the table is being supported by a surface right here, pushing up on the table. But let's relabel that. Look at this. So this is a force of the Earth pushing up on the table, so also known as force of Earth on table. Force of E on T, force of Earth on table. Okay, so we're starting to label forces, or at least talk about them and look at them as so that we can understand, well, the force of what acting on what. It's caused by one thing that's acting on another, right? I haven't done that with these forces. This one, also known as force of, it's a force acting on the vase, but what's causing this? The Earth. Earth on vase. This one, also known as force of Earth on table. That's interesting. Uh-oh, that might get us into trouble. So I'm not sure I'm real keen on that any longer for the weight, for this particular force. We'll see where this takes us. If that causes a problem, then we'll figure something else out, right? We can always just call it weight. It is caused by Earth, but it's not a contact force. Okay. Well, there's one thing I want to point out to you, and it is this. That in this whole entire group of forces, we have two objects interacting with each other, the table and the vase. And when they interact with each other, that's when they create these forces between them. So we see force of table on vase right here. And let's look at the opposite of that notation. Let's look for the vase on table, force of vase on table, this one. And here's the deal. Here's what Newton's third law really, really says. That you can't get one without the other. Forces always occur in pairs. So this is where we're going to wrap up this video, just looking at this simple example. We have, let me make sure I connect those. Those two forces are what are sometimes called a force pair. I call them twins once in a while. Now, we'll look at those. So about Newton's third law. So some things to write down. Make sure you remember this stuff. Forces always occur in pairs. Now, as a side note, some people would actually describe that pair of forces there and there as not a pair of forces, as a single force. That single force is affecting these two objects differently, but it's still just a single force. It's one way to do it. You'll see it like this most of the time, as forces occurring in pairs. Those forces in a pair, in a force pair, I sometimes call them twins, by the way. They're force twins. They always act in opposite directions. Come on, paper, hold still. So forces always occur in pairs. They always act in opposite directions, so you can see that right here. And there's one more very important thing that's often unsaid. The two forces in a pair, or the two forces in that set of twins, always act on different objects. And that's often overlooked. So those three things about Newton's third law are really important. You've heard Newton's third law before. For every action, there's an equal and opposite reaction. But that's nice and it's easy to remember, but it doesn't mean a whole lot. Here, for every action, there's an equal and opposite reaction. Yes. Forces always occur in pairs. So we have the two always act in opposite directions, so we got that. And they always act in different objects. That's real important. This half of the pair is acting on the vase. This half of the pair is acting on the table. So you always want to look at these three things. Always, always, always. Now, does that mean that these two objects are affected in the same way by these two forces? Not at all. Not at all. We'll see that. The effect of the force might be dramatically different. And you'll see that, thankfully so. Thankfully that's the case. Otherwise we'd have a real hard time putting objects into orbit, sending them into the moon, getting groceries to your table, just about everything. So anyway, that's it for now. Newton's third law of motion. Remember these facts about it, and we're going to work on it. Thanks for watching. I'll catch you next time.